Okay, so before we get into the whole concept of the periodic table and nomenclature, with the bulk of today's lecture is about, I want to introduce this little thing called the law of multiple proportions. This is kind of a new concept for the AP exam. It's never really been tested on before, so I've never really taught this before. And I don't think it's going to be huge on the AP, but I do want to introduce it to you and do a really simple little example of how this works. First, let me define it, and that'll help you understand it a little bit better. The law of multiple proportions says that if two different elements combine with a set weight of one element, their ratios will be small. I wrote same. How did I write same and say small? That's pretty impressive, actually. Will be small whole numbers. The example I'm doing right now is going to be the level of difficulty I expect you to understand. Right now, before we even do this, I'm going to give you a pass. Tomorrow night's homework has problem 9 and 10, which are really, 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 really challenging. I can't even stress that. So if you struggle on tomorrow night's homework, those last two problems, I'm giving you a pass. If you want to come in and work with me, we can go through them, but they're really hard, and I'm not going to hold you accountable for that level, okay? This is where we're going with this, and this is all I need you to know. So the first thing I want you to look is, you look at the table, we're going to demonstrate this whole number ratio thing through the use of this data. So we're going to, in this case, realize that each compound is composed of nitrogen and oxygen, okay? We're going to make nitrogen green. Well, I'm going to make nitrogen green and oxygen blue. Okay. So in each case, we are combining a certain amount of oxygen, a certain amount of nitrogen with a set 1 gram of oxygen. So compound A mixed 1.750 grams of nitrogen with 1 gram of oxygen, and so on and so forth. Got it so far? Are you kind of with me? Now, the next thing I want to do is compare my nitrogens and how they're different in each compound. The amount of oxygen is the same, so we don't have to really look at the relationship. But for instance, let's go from compound B to compound A. What happened to the number? What happened to the amount of, proportionally to the amount of B to A, nitrogen? What happened to it? Well, yeah, it increased, but let's be more specific. It doubled. Do you see how it doubled? Okay, we're dealing with the whole number ratio thing, so we want to look at whole number ratios and see how ratios change. What if we go from C to B? What happened to the amount of nitrogen there? It doubled. What about C to A? It quadrupled. Okay, so we did basically that thing. So that's going to give us the key to this issue. What we need to present, possible formulas for these things in relationship to one another. The true answer to this problem is unlimited. Well, there's actually 9 different answers, but we're going to just start somewhere and stick with it. So what I'm going to do, because I kind of know how this problem and where it's going, arbitrarily, I'm going to go ahead and pick compound B first. I'm going to start with compound B. And I'm going to say, okay, in my arbitrary compound B, I'm going to say it is 1 nitrogen to 1 oxygen. If it's 1 nitrogen to 1 oxygen, I'm arbitrarily assigning it 1 to 1. What would the formula be? NO. Y'all see that? I'm just deciding that. You can make any of them 1 to 1. I'm just making B 1 to 1. And remember, we're going to present possible formulas, and this is all in relation to each other. Okay. So if this is compound B, what would compound A turn out to be? So let's look. In compound B, we had 0.87, but here we had 1.7. What happened to the amount of nitrogen? The amount of nitrogen doubled. Since the amount of nitrogen doubled, I'm going to have 2 nitrogens to the 1 oxygen. You see how that proportionality works? Okay, so what would the formula for this be? N2O. Nice. Now, compound C is where it gets a little bit tricky. Okay, compound C, remember, we're starting with B as our 1-to-1. That's our standard. If you look at compound C, what happened to nitrogen? It cut in half. Can I have a half of an atom? No. Since I can't have a half of an atom, what can I do to take care of that ratio of oxygen to nitrogen? 2 oxygens. Perfect. Y'all get this. 2 oxygens to the 1 nitrogen. So what would its formula be? N2O. Okay, so this, oh, my bad, NO2. This is I get from listening to the crowd in front of me. NO2. I'll pick up on it, on someone saying something. No idea if it's right or wrong. I'll just write it because I don't think. All right, so NO2 would be the answer to compound C. So again, these answers kind of come as a grouping, because these would be totally different if I made another one 1-to-1. So if you look at the next slide over, come on, let's move. We chose 1-to-1 to be this, so this is what we just did, okay? In this slide, they chose A as 1-to-1. If you notice, from B to A, what happened to that nitrogen? The nitrogen was cut in half. So instead of cutting the nitrogen in half, we double the oxygen. From C to A, what happened? It was divided by 4, right? So we couldn't cut the nitrogen in 4. Instead, we had to quadruple the oxygen. Okay? So that would have been a possibility, but I was lucky enough to choose the easy route. So Grant just asked me if on a test would I accept any 3 sets, any 3 in a set. I would, as long as their proportions to each other are accurate. Okay, because that's what you're proving the identity of, that law of multiple proportions. Who the heck would do this? So I call this stupid. I would never have gone here in my head. It's right, but I wouldn't have gone here. So we're going to pretend we don't see that. This is the level I expect. It's going to be this simple on the quiz. It's going to be just as simple on the test. I'm not going to give you a scary one like you have in your homework. Those are from the challenge portion of a textbook, just to extend your brain. Some of you might nail it and might really get it, and I struggle with those 2 because I just don't think very well in this type of way. All right? So we're keeping it simple. KISS. Keep it simple, stupid. I'm not calling you stupid. All right. They're actually smiling, people at the audience. I'm not being mean to my students and calling them stupid. Periodic table. We're going to fly through this. Now this is the true review time where we get to see things we haven't seen in a while. So you guys are going to be responsible for knowing all the main parts of the periodic table. You got to know your groups. What group is this first one? Group is up and down. Alkali metals. The next one, alkali earth. All these in the middle, transition. These down here, rare earth, intertransition. There's different ways to name them. Over here, we've got our non-metal metal line, which kind of just goes like this. You all know where that is, right? Okay. Then we get to nitrogen group. Oxygen group is also sometimes known as the chalcogens. What are those? You got to know group 7. Halogens, and these babies on the end, noble gases. Okay, sounds like you all know your periodic table. Now, as far as the parts of the periodic table, on the periodic table, every single box has one of these numbers. What is that number? Atomic number. What does that stand for? This is number of protons, sometimes seen with a Z. That's the identity of the element. If that number changes, the identity of the element changes, okay? Down here underneath, you've got some numbers with decimal places. What does that number represent? Atomic mass. What can I find out from the atomic mass? Oh, I heard someone say number of neutrons or protons. I set that up on purpose to sting you and to catch you, because how can you have a point something of a proton or neutron? What does the atomic mass actually represent, or the atomic weight? Nice, the average of all the isotopes, okay? So the isotopes, which have different number of neutrons, have their own weight, and then they take the average and get the average atomic mass. What is this average atomic mass or atomic weight also the mass of? No, not 1 gram. 1 mole. This is also known as the molar mass, or grams per mole, right? So carbon, there's a 12 up there. Carbon, there's 12 grams. 1 mole of those carbon atoms means there's 12 grams, okay? What would I need to actually figure out the number of protons in the nucleus? The number of, no, we know the number of protons. I have to be given more information. What would that be? The mass number. That's, who said that? Nice, good job. There's something called mass number. Mass number is a whole number that is specifically how many protons and neutrons are in an isotope, are in which isotope, okay? How you're going to see that is through a version of this. The number on top, notice there's no decimal places. This is a condensed formula to figure out, given the mass number, so we can figure out everything up there. So we're going to go ahead. I'm going to add an E, and I'm going to do 14.14 over 7. No, not 14. Yeah, 14. Nitrogen as well. I'm going to add that. And I'm going to kind of make a chart here. We're going to find protons, neutrons, and electrons down this whole page. Okay, so silver, that first one. How many protons are in silver? 47, because that's the atomic number. How do I find neutrons? Subtract 109 minus 47. What do I get? 60 what? And then number of electrons, 47. How did I know that? Why is it the same as the atomic number? It's a neutral atom. Sarah got that. It's a neutral atom, so it's not going to have a charge. So there were 2 atoms walking down the street. One atom says to the other, hey, someone just stole an electron. And the second atom's like, are you sure? How do you know? The first atom's like, I'm positive. Get it? Okay. First period laughed a lot more than you did. Neutron walks into a bar. A 21-year-old neutron walks into a bar and says to the bartender, hey, how much for a beer? And the bartender's like, for you, no charge. Okay, whatever. Y'all are horrible. Last joke I ever tell in second period. Okay, magnesium, how many protons? Neutrons? 12. Electrons? 12. You got this 12 from subtracting, right? Okay. I know somewhere in middle school somebody told you if you didn't know the number of neutrons, make them the same as the protons. Yeah, no. Not good. No bueno. All right, aluminum, how many protons? How many neutrons? And how many electrons? 13. All right, now we're getting into some chargedness going on. This is a positively charged atom. What was a positively charged atom called? Kinsey! A cation. For those of you at home, one of my students' last name is Cation, which is mispronounced because it's really cation. And it's actually spelled the same way, so she is Kinsey cation. So how many protons do we have? 47. How many neutrons? 60. Okay, this is where we got to be careful. Never, ever, ever, ever touch the protons to make something charged because that changes the identity. We just have to futz with the electrons. So if we're a +1, we need 46. We need one more positive than we do negative. Okay, nitrogen. We've got an ion here. What is the negative ion called in our world? We just had a cation. Can't have both. These are both ions. One's this one and one is an anion. Okay. Protons. Neutrons. How many electrons? Okay, so I think y'all are good with that, right? Okay. Now we get to look at the periodic table and talk about the charge some of these atoms make when they turn to ions. There's going to be quite a bit of memorization here for those of you who were not in pre-AP. If you were in pre-AP, or even if you were in regular, y'all remember that you had a list of things like iron can be +2 or +3, all that. So if you were in pre-AP, you've already memorized them once. I'm just going to remind you, if you were in regular, you got to make some cards now and start the memorization process. We're not going to be doing the old system of nomenclature for those of you who are curious, just because it's not on the AP and it's slowly going out of use. So first I want to start with my ions and anions, cations, all the ions that have only one possible oxidation state or one possible charge when in a compound. If you get a chance, everything I'm telling you now, I want you to go download the periodic table that you have in the general information folder on the website and translate all the stuff I'm giving you to location on the chart. I don't memorize stuff by a list. I memorize by chart location. All right. So looking at group 1, when group 1 metals make charges, what is that charge? Group 1. +1. When group 2 stuff, oh, and I wrote 2. I did that last period. All right, +1. What does group 2 do? +2. Now, transition metals we're going to skip because all of those and all their d electrons are going to have multiple charges. So we're going to move on to where aluminum is. That's group 3. Boron above aluminum does covalent bonding. It doesn't make charges. So I'm going to say it's safe to say the only thing we're talking about in group 3 is actually aluminum. And what is its charge? +3. Now we're going to skip the carbon family because lots of covalent action going on there, lots of confusing stuff. Moving on to nitrogen's family. So I'm going to call it the nitrogen group. What are those? What? -3. And then oxygen, also known as the chalcogens. What are they? -2. The halogens, -1. And noble gases, if they bond at all, it's larger ones, and those are in covalent situations, so they don't form ions. All right, now let's, there's a couple more that are also single. I want you to notice on the table how aluminum drops to zinc, drops to silver, kind of in a stair step. You'll see that? Aluminum is +3, zinc is +2, silver is +1. Those only have one charge. Does anybody remember cadmium? Cadmium and zinc are both +2 because they are on the chart together. Okay? There is, let's see. Yeah, those are the only univalent, the ones that only have one charge that you need to know. So I expect you guys to know all of that. Now let's talk about the multivalent stuff. I do these in grouping on the periodic table. Iron, cobalt, nickel. See how they're all together? Okay, I see those as a group. I don't know these, like this I do because I just wrote it down, but like when I'm trying to figure out the charge of something, I myself am looking, okay, 10's there, I know what it is based on where it is on the table. So it really helps you looking at location. So this is, who remembers? +2, +3. Good. what about, we'll do copper and mercury because they both have the same situation. +1, +2. There's high fives going on in the back. Now, let's talk a little bit about mercury. Mercury is a little bit special. When mercury is +1, it's actually a diatomic. Y'all remember that? I know they taught it. Mercury can only be +1 if it's like that. Mercury's +2, though, is like this, so that's okay. So just know mercury can only be +1 in the diatomic fashion. All right, how about gold? AU, this is gold. Yes. +1, +3. What about, I want you to look at these two groups. There's tin and lead, and then next to it, antimony and bismuth. So I look at them, boom, 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 left to right. Tin and lead, anybody? +2, +4, then this is +3, +5. Larson is way too excited about his memory. One thing I do want to point out, arsenic here, when it acts as a metal, it will have a +3, +5 option, but sometimes it does weird things, so if it bonds covalently, it won't. Just know that that's an option. Did I miss any of them to your recollection? I don't think I did. Okay, so now we're going to apply all this to binary nomenclature. Okay, today we are only going to name things that have two different elements in them. Just, they can have multiple numbers of those elements, but only 2 elements. So what does that mean our compound nomenclature today won't have in it? Polyatomics. So I'm giving you a heads up tomorrow to be prepared, either study the polyatomics or print out the polyatomic sheet and have it in front of you to make class less painful for me, because it's all about my comfort. I'm just kidding. You do need to start on those pronto. Starting tomorrow, I'm assuming you know them. But today we're doing binary nomenclature. In binary nomenclature, I want you to go through a series of questions before you name them. The first question is always, is there a metal present? In other words, is it ionic or covalent? If there is a metal present, it's ionic, and we name it exactly as we see. If it's covalent, there are only nonmetals in it, and we use prefixes, mono, di, tri, and so on. Okay, so you're going to get sick of me. The first question I'm going to ask every single time is ionic or covalent, ionic or covalent, ionic or covalent, and you have to answer that question. Okay, then I'm going to ask you a question. If it is ionic, can the metal have more than one charge? If the metal can have more than one charge, what do we need? No, we need something in there to tell us what the charge is. Roman numerals, maybe? Remember that? So that's what this little flow chart's telling you. If there's a metal present, does the metal form more than one cation? Yes, we need Roman numerals. Okay? All right, so everything on this list, nicely enough, is all ionic. So this is a list. You see how they're all metals and non-metal combinations. That's not going to happen all the time. You know, I'm just giving you practice here. So since they're ionics, we just name what we see. And if it's a metal that has more than one charge, we put in a Roman numeral. Got it? Now, there are 3 possible endings for a compound: "ide," "ite," or "ate." If it comes from the periodic table, if that second ion comes from the periodic table, it's an IDE ending. Where do I get the ites and the ate endings from? Polyatomics, okay? So today we're just doing the ides. All right, let's start with the first one. What's this one called? Sodium chloride, because sodium only has one charge, we don't need a Roman numeral. So sodium chloride. Next one, potassium sulfide. Why isn't it dipotassium sulfide? Because it's not what? It's not covalent. And the thing about this is, if you put potassium and sulfur together, this is the only possible charge, only possible formula it could be. So that's why we don't need to use any sort of descriptor of the amount that we have. All right, the next one. Aluminum fluoride is spelled not flour, it's fluoro. Aluminum fluoride. I won't freak out on you with spelling. Like if you did fluoride instead of fluoride, I'd be okay with that. I will freak out on spelling if it affects the name of the compound, nitrite versus nitrate. You can't say, oh, I just misspelled that. No. And I also, in situations like manganese versus magnesium, so I have a hard time with people writing down magnesium, and it happens. So in those situations, spelling does count. This next one, what can you tell me about cobalt? It can have more than one charge, so I have to indicate with a Roman numeral what the charge on the cobalt is in this one. What is it? Because there's 3 iodides, each one of those is a -1, so it's cobalt 3 iodide. Calcium, does it have more than one charge? No, so what's this called? Calcium what? Bromide. All right, copper, does it have more than one charge? Yes, what's its charge here? 2. Y'all got that. Each nitrogen is 3, excuse me. There's 2 of them. That makes this side -6. So this side has to be +6, but there's 3 of those, so each one is a 2. Or you could just uncrisscross. But be careful, uncrisscrossing doesn't always work. Be very, very careful. Because if I had Hg2O2, you couldn't say mercury was 2. Because in that case, mercury is 1. So be really careful. Copper what? Nitride. All right. Silver, more than one charge? Nope. So what's this called? Selenium, selenide. All right. Tin, more than one charge? Yeah, so what's it here? Tin 4, good buddy. Tin 4 what? Sulfide. Good. Next up, look at this grouping. Oh, I'm so short. I'm going to pause this. Okay, the first one, calcium sulfide. What's the formula? CaS, because calcium is +2 and sulfur is -1. All right, I'm going to go across just so I can get off the stool faster. Barium fluoride. Barium is +2, fluoride's -1. What's the formula? F2. Cesium hydride. Don't let hydride scare you. Look at hydrogen. Where is it on the table? Above. So what would you kind of assume its charge to be? +1. But cesium's +1, right? So when that's the case, slide hydrogen all the way over till it's above fluorine. What would it be there? -1. Hydrogen it is where it is, and it's the only one there because it has aspects of both families. Okay? So in that case, it's going to be what? What charge? -1. So this is a +1, this is a -1. We get CSH. Another indicator is that it's in the second spot in the actual compound, and we always do our pluses and then our minuses in these. All right, lithium phosphide. +1, -3, what's the formula? Li3P. All right, copper 1 oxide. What is that Roman numeral telling us? The charge on copper. So copper is +1, oxygen is -2, so what's the formula? Cu2O. Good. Bismuth sulfide. Bismuth 5. So what is the 5 the charge of? Bismuth. Sulfide is what? 2. So what's the formula? That was a big high five. All right, going on to the next one. Nickel 3 bromide. Nickel is +3, bromide is -1. So what is this? NiBr 3. Cadmium nitride. Oh, cadmium doesn't have a Roman numeral. It must only have one charge. What is that charge? +2 -3, so it's N2. Okay, good. So now we get into the different world, the world of covalent nomenclature. Again, the world is not so organized where you're only going to be asked one type at a time, but for reminding purposes, all I have in problem 13 are covalent compounds. Looking at these, we are going to review the prefixes. I want you to know 1 through 10. So if I have 1, it's mono. 2, I can't hear you, really loud. 3, louder. 4, louder. Thank you. 5. 6. 7. No, not septa. Septa's geometry. Hepta. 8. 9. Non, nona. And then 10. Deca. So you need to know those to do these problems. In the first one, I know we only have 1 in that initial spot of nitrogen, but we don't use mono if we're talking about the first element, so we just say nitrogen monoxide, okay? Nitrogen now, there's some rules about the naming that I'm not even going to worry about because they're so inconsistent. But if there's supposedly if there's 2 vowels that are the same right next to each other, you only use 1. So instead of saying monooxide, they say monoxide. And then there's some crazy rule. If you have 2 vowels together and they're not the same, you drop the second one. Whatever you do, as long as I can see you know what's going on, it's going to be fine. What is the name of this one? Nitrogen dioxide. Next. Dinitrogen tetroxide. Tetroxide. Again, I don't care how you write it. If I know it's a tetra and I know you have an oxide together, if you drop the O, drop the A, whatever. I think that's a 3 under the P. All right, what's that called? Triphosphorus pentanitride. Up to the top of the next row, column. Sulfur trioxide. Next, tetraphosphorus decaoxide or decoxide. Nitrogen trifluoride. Carbon tetrachloride. Okay, last few. These are going to be a little bit mixed up. So let's see how you guys handle that. Silicon dioxide. Boron trichloride. Xenon tetrafluoride. Phosphorus pentabromide. Barium fluoride. Okay, we're in ionic world here, right? Does barium have more than one charge? More than one charge? No, so it's BAF2. Lithium phosphide. Tellurium tetraiodide. Oh, we shifted gears. That's covalent. Fe. Okay, and then sulfur dichloride, SCl2. I think is that it? Yeah. Okay, so I know I flew through those. Okay, this is one of those areas that I assume you guys learned in Chem 1. And if you feel like you need some extra help on this, do the homework, go to the textbook, do some more. They have all the answers to all the odds in the textbook. So you can go to the end of the chapter, do some more from the textbook, and then come and ask me specific questions about problems that you didn't know the answers to. And I will help you through those. But it's one of those things that if you're behind, you've got to review this on your own. This is the language of our class. Without it, you are, oh boy, it won't be good. Okay? All right, so start working on your homework for the rest of the period.